Hello, my name is Tirana Norfatianusa, and I'm a graduate student at Kumamoto University, Japan. Today, I would like to present our paper entitled Effects of the Number of Hyperparameters on the Performance of GACNN. Here is the outline of my presentation. Introduction. The performance of machine learning algorithm is highly dependent on its hyperparameters. However, hyperparameter optimization is problem-specific and its quality depends on the training process results. For example, we have a set of hyperparameters and we aim to find the right combination of their values, which can help us to find either the best performance. One of the most popular and widely used hyperparameter optimization methods for deep learning is deep neural evolution, which employs evolutionary algorithm to drive the learning process. In this paper, we focus on optimizing a convolutional neural network, or CNN, using a genetic algorithm, or GA, in an automated way. Hyperparameter optimization is not a trivial task, and the difficulty increases when coupled with a larger number of hyperparameters as faced by deep neural networks. There are two research questions that we try to solve in this paper. The first is, what is the effect of the number of hyperparameters in GACNN? For example, we select the hyperparameters and optimize it using GACNN and analyze whether the more hyperparameters that are optimized, the better the performance. The second research question is, what is the effect of the number of optimized hyperparameters in GACNN? In this paper, we investigate the performance of GACNN using the same hyperparameter for each layer and different hyperparameters for each layer. For example, we have architecture that consists of 3 convolutional layers and 2 max pooling layers. In the first sim, all convolutional layers and all max pooling layers will have the same hyperparameters. Meanwhile, in the latter sim, each convolutional layer and each max pooling layer will have their own hyperparameters. Related work. The well-known approaches utilized by practitioners to optimize hyperparameters are grid search and random search. Grid search tries all combinations within the sets of values, while random search randomly selects a subset of combination within the defined range. However, every solution in those approaches is independent because there is no mechanism to learn from previous search. On the other hand, evolutionary algorithm offers a learning mechanism to ensure the algorithm to jump out of local optimum in high search space dimensions. Owing to this ability, some research utilize evolutionary algorithm, and most of them use genetic algorithm and utilize a small number of hyperparameters ranging from 2 to 9 hyperparameters. And the number of hyperparameters optimized in our paper is the highest compared to those papers. CNN hyperparameters and architecture. The optimized hyperparameters were divided into 3 categories: global, layer, and architecture hyperparameters. Global hyperparameters are those that influence the overall model, while the layer hyperparameters define the hyperparameters at the layer level, and the architecture hyperparameters determine the depth of the CNN. The global hyperparameters consist of 5 hyperparameters, and we define the range or the list of values, and we also define the default values for each hyperparameters. Layer hyperparameters consist of 13 hyperparameters. Other than the common hyperparameters, we also optimize the output dimensions in embedding layer and maximum width constraint in convolutional and dense layers, which to our knowledge, there have been no paper optimizing it. Our GSNN also optimized the depth of the CNN architecture by determining the number of convolutional and number of dense layer. All the hyperparameters were optimized with a fixed CNN layer order from the input to the output layer. So the GSNN only optimized the hyperparameter values and architecture's depth by determining the number of convolutional layers and the number of dense layer. A global max pooling layer follows the last convolutional layers, while max pooling layer follows each of other convolutional layers. Therefore, the number of max pooling layer is the number of convolutional layers minus 1. GSNN. The logical flow of our GSNN starts from the pre-processing of the training and validation data, and then optimize the hyperparameters and the architecture of a CNN by using GA. From GSNN, it produces the best architecture and hyperparameter values. Inside a GSNN, it consists of genetic algorithm processes and also the CNN. The GA consists of 5 processes: population initialization, evaluation, crossover, mutation, and selection. The evaluation process forwards the generated architecture and hyperparameter values to the CNN. After that, the CNN returns the fitness value. A fitness value is produced from a fitness function, which is used as evaluation function of each individual in the GA. The population initialization consists of 2 types of chromosomes: hyperparameter chromosomes and architecture chromosomes. All the individuals will have the same chromosome length for the hyperparameter chromosomes, regardless the generated value of the MC and MD. For the architecture chromosome, as stated before, the optimization used a fixed layer order, and we optimize the depth of the CNN by determining the number of convolutional layers and dense layers. So the chromosome length for the architecture will be diverse. In this paper, the F1 score is utilized as the fitness functions. And the crossover operator performs differently for different types of chromosomes. For the hyperparameter chromosomes, we use 1-point, 2-point, and uniform crossovers, which were selected randomly. And for the architecture chromosomes, we use 1-point crossovers with a global max pooling layer as the cutting point. As for the mutations, we use uniform mutation for the hyperparameter chromosomes, and architecture chromosomes is mutated by adding or removing a convolutional layer or dense layer. And the best individual for the next generation is then selected using elitism selection. Results and discussions. The disaster tweets dataset from Kaggle competitions was used to assess the performance. And disaster tweets datasets is a supervised text classification problems that classify sentence into 2 classes, relevant and not relevant. The portion of the dataset is 49% for training, 21% for validation, and 30% for testing. The chosen values for crossover rate was 0.8, mutation rate is 0.2, and the select generations, number of generations and number of population were equal to 30. The comparison consists of two parts, training and testing. In the training, we find the best architecture and hyperparameters from GSNN. And in the testing, we test the best architecture and hyperparameters from GSNN using test dataset. We compare 7 experiments with different number of hyperparameters and different numbers of optimized hyperparameters. The number of hyperparameters refers to hyperparameters within this list. The number of optimized hyperparameters depends on whether each layer will have its value or not. Layer hyperparameters with 1 star means that the hyperparameters was selected once and the same for all layers. And layer hyperparameters with 2 stars means that each layer will have its hyperparameter values. As can be seen, the GSNN obtained the highest best and highest average F1 scores over other methods. However, the GSNN requires a higher execution time owing to several operators that need to be executed. But the extra time is still acceptable as the GSNN can obtain higher results, the highest results for all the experiments. This table also demonstrates that the best F1 score for experiment with 1 star, experiment 2, 4, and 6 turned out to be on par with experiments with 2 stars, experiments 3, 5, and 7. However, from the box plot of the final F1 score from 5 runs, the mean values for experiments with 2 stars are higher than the mean values for experiment with 1 star. The box plot trend is going up after investigating different hyperparameter values for each layer. This means that the 2-star experiments can get higher best F1 score than 1-star experiments if higher number of generation, higher number of populations, or higher number of runs are executed, which is beyond the scope of this study. And the box plot of the F1 score rose gradually from experiment 1 to experiment 7, and a monotonic increase in F1 score for experiment 1 to 7 is in line with the addition of the hyperparameters. Another difference that can be discussed is the relationship between the solution during the search process. As can be seen from the plots, most of the results of grid search and random search were 0. Apart from that, no other pattern could be learned because each solution was independent. The TPE was also trapped into a local optimum, even though there are dependencies on its iterations. Meanwhile, the graph of the GSNN and TPOT goes up every generation. However, the F1 scores of TPOT cannot outperform the GSNN. The generated architecture for all experiments are quite small, consists of 6 to 9 layers. In the testing, the GSNN surpasses other optimization methods. However, all the CNN optimization methods fail to achieve higher value for experiment 1. We also compare our approach with several submissions for the Kaggle competition by calculating the F1 score from their submission file. And the GSNN outperformed those submissions. We also conducted a Wilcoxon-signed rank test. As can be seen, almost all the results of the GSNN pairs demonstrate statistically significant difference in training and testing, except of the pairs of experiment 1, 2, 2, 3, 4, 5, and 5, 6. Experiment 7 has statistically significant differences when paired with other GSNNs. This finding is evidence that the GSNN with a larger number of hyperparameters is better than the lower one. Conclusions and fieldworks. The results from 7 experiments show that a larger number of hyperparameters and layer-specific hyperparameters values are important. The Wilcoxon sign rank test also exposed the superiority of the GSNN with a larger number of hyperparameters. The GSNN produced higher F1 score than other methods in training and testing. The optimization of the output dimension and maximum norm weight constraint hyperparameters has a notable impact in the search process, especially when different hyperparameter values for each layer are investigated. In this paper, we use static CNN architecture. In the future, it is interesting if we can use dynamic CNN architecture design to achieve higher adaptability over different problems. It is also interesting to select important hyperparameters automatically and optimize them, as important hyperparameters may have more responsibility in performance improvement. In this study, the crossover rate and mutation rate were determined using trial and error. In the future, those values should be able to adapt based on the present situations. While we have shown the effectiveness of our approach by using standard GA, further comparisons should be investigated to gain more insight from the proposed approach. Thank you for your attention.